Your bridge was built to last 50 years. The building you're in right now has a designed lifespan of under a century. Roman concrete sea walls and harbor piers are still standing after 2,000 years. The Pantheon's dome, unreinforced, never maintained, has survived every major earthquake Rome has had. Scientists thought they knew why. Volcanic ash mixed with lime, that was the secret. A 2023 study by researchers at MIT proved that answer was incomplete. The full story is far stranger. When Rome wanted to build at scale, stone wasn't enough. You can only stack stones so high before the structure collapses under its own weight. Rome needed something that could be poured, shaped, and set underwater. Around 15 BCE, an architect named Vitruvius wrote it down. Volcanic ash from the Bay of Naples, lime, seawater. Mix those together, and you get a material unlike anything built before. It sets underwater, which no cement in the ancient world could do. It doesn't weaken over time. It gets stronger. The ash is packed with minerals that chemically bond with lime the moment they touch water. What starts as a wet mix slowly becomes something closer to rock. By the 1st century BCE, Rome was a Mediterranean power. That meant harbors, massive breakwaters stretching into the sea. And that presented a problem no material had ever solved before. Modern concrete uses steel rods inside for strength. But seawater carries salt, and salt makes steel rust. Rust expands. That expansion cracks the concrete from the inside out. Modern concrete in seawater is quietly destroying itself from the moment it's poured. Roman concrete did the opposite. Seawater triggered new chemical reactions inside the structure. Minerals grew between the volcanic ash particles, filling gaps, knitting the mix tighter. Roman harbor breakwaters, built 2,000 years ago, are still intact today. The longer it sat in seawater, the stronger it became. But there was something in Roman concrete that confused scientists for over a century. White lumps scattered through the mix everywhere you looked. Rich in lime. Clearly undissolved. The explanation was immediate and unanimous. Poor mixing. The Roman workers hadn't done their job properly. For over 100 years, that was the consensus. Early archaeologists used this as evidence that Roman construction quality was inconsistent. Then in 2023, a team of researchers at MIT examined those lumps more carefully. They weren't evidence of incompetence. They were the most important feature of the entire design. Quick aside, this kind of reversal is what this channel hunts for. Wrong for a century, right all along, there are dozens of those stories here. A like tells the algorithm this one is worth finding. A follow does the rest. The Romans were using a technique researchers now call hot mixing. Instead of adding water to the lime first, which is the standard method, they skipped that step. They mixed raw, dry quicklime directly into the volcanic ash, while both were still blazing hot. Quicklime is the powdered form of lime before any water is added. When water touches quicklime, the reaction is violent. It generates enormous heat. Mixing it dry, at extreme temperature, left something behind in the structure. Small chunks of undissolved lime, scattered throughout the entire matrix. Like tiny sealed capsules, embedded throughout the whole structure. Now imagine a crack forms. It happens slowly, a hairline fracture working its way through the stone. Water seeps in. That water reaches one of the lime capsules and dissolves it. A calcium-rich liquid is released into the crack. That liquid meets the volcanic ash lining the crack walls. A reaction starts. A mineral begins to crystallize. It fills the crack, it seals it shut. The concrete fixed itself. Without anyone knowing a crack had formed. Without anyone touching it. The same mineral that forms in seashells was crystallizing inside Roman walls. There's one more effect the design produced that nobody planned for. Modern concrete is rigid. When seismic energy hits it, it shatters. Roman concrete is porous and modular. Seismic energy enters the structure and gets absorbed and distributed. The Pantheon has been through over 2,000 years of seismic activity. Its dome has never cracked. Now step back further. Modern cement production is responsible for roughly 8% of global CO2 emissions, 8% of everything humans emit every year. Roman concrete, volcanic ash and lime, produces a fraction of that. Inside Roman concrete, over centuries, rare stable minerals slowly form. We can barely reproduce those minerals in a laboratory today, even with modern equipment. The Romans got them through chemistry happening at room temperature. The research today focuses on substitutes for Italian volcanic ash. Ash from coal plants, powder from steel mills, industrial waste that might replicate what volcanic ash from the Bay of Naples does. The chemistry is solvable. The harder problem is the building codes. Modern construction regulations are written for concrete. That stays the same. We moved from building for centuries to building for decades. The Romans viewed a structure as a permanent contribution to the state. We view a structure as a depreciating asset on a balance sheet. Modern concrete was engineered to resist the environment, to stay inert, to hold firm. Roman concrete was engineered to work with the environment, to react, to adapt, to grow. One philosophy produced structures that last 50 to 100 years. The other produced structures still standing 2 millennia later. We didn't improve on the Romans. We just moved faster and louder. And we lost 2,000 years of durability in the trade. The Romans didn't build concrete to last. They built concrete that knew how to last. There's a difference. Every crack in a Roman harbor is already being fixed from the inside, in the dark, without anyone watching. More of this kind of thing next time.